All right, hello everyone. How are we doing today? So this is going to be the exam 1 review session. So this is something new I'm trying. Typically, I used to do this just by streaming, but now I'm just going to record it and upload it to Canvas for you all. And that way you have something to reference and watch before the exam. So I hope this helps. So remember, exam 1 is on chapters 1 through chapter 5. Apologies if my handwriting is bad, but you have the audio and the captions up down below if they can help. So here, chapters 1 through chapter 5. So getting right into it for chapter 1. So chapter 1 discussed the unifying themes in biology. So there are 5 main themes of biology. We discussed all these in chapter 1. So 1 is organization. So we are all organized a specific way. And let me write organization. So from the top down to bottom up, populations versus communities. Understand the difference between a population and a community. They're talking about different things. One is larger than the other. So a group of organisms that belong to the same species within a defined region is called a population. And then that region itself is the community. And then the biggest region available is then the biosphere. So first here, so we have organization. It can be organization based on, biosphere versus population, or organization based on the systems in our body, the different cells that make up the tissues, that make up the organs, which make up, the cardiovascular system then, and so forth. And all those work together and are organized in a specific way to function correctly. So there's organization, and then there's information storage. We'll just write this as information. So information then is the genetic material, RNA, DNA, being able to pass that to offspring, and so forth. Then we have evolution. So the ability to evolve is very important in organisms. So if you can't evolve, your species isn't going to survive. You have to be able to adapt to environmental changes because those changes are going to occur. The next one is energy transformation. Oops. So energy transformation, something like plants converting sunlight, draw this arrow bigger, using sunlight to make chemical energy. That chemical energy is then broken down by us. So then this goes through cellular respiration, which we'll talk about later, to turn it into kinetic energy by using ATP. So this chemical energy here would be something like glucose. We then break down glucose to make ATP. So this is all an energy conversion process. And throughout this whole process then, at all these stages here, heat is being removed. So heat is always lost to the surroundings during energy transformations. So energy transformation is a very, very important one right here. And we have some chapters coming up that define this energy transformation. And 1 second here as I search for something. I need to pull up a lecture. First lecture here just to make sure I don't forget anything. And boom. So now, what's the last one? So there are 5, remember. This one is now interactions. So we interact with our environment interacts with us. So that interaction can be both positive and negative. Within our body, we have our own interactions. We have positive and negative feedback. So an important one under this one is positive versus negative feedback. So make sure you understand the difference between positive and negative feedback. A good example of negative feedback would be insulin control. So when you eat sugar, your blood glucose rises. Your body then has a feedback mechanism that says release insulin to decrease the amount of sugar in your blood. And then that feedback mechanism goes through, releases insulin, blood sugar decreases, and then you need to shut it off. So then insulin is then stopped being released, which is negative feedback. Don't think of negative feedback as something that's bad. So it's not necessarily bad. It's just used so your body conserves energy and you don't release too much insulin. So those are the main unifying themes in biology, because life defies a simple one-sentence definition. So let's see here. Okay, also, let's say, talking about how life is organized. So we're going to hit on some of these themes as I go through, and remember some things I need to mention here. So organization levels here. Let's draw a simple clade diagram. So we come out and we have a branch right here. And then let's say this one branches again, and then this one stays straight. So here we have bacteria. This one is archaea. And this one, AEA. And this one is eukarya, which is us. So these are the main domains of life. So now, what is A? So A is the common ancestor. And B, let's say this is the branch point here. This is B. B is then the common ancestor of archaea and eukarya. So A is the common ancestor of all life, whereas B is common ancestor of archaea and eukarya. So I'll just abbreviate this here and just to freehand it. So B is the common ancestor of archaea and eukarya. So make sure you understand what these different points on these clade diagrams here. So then every point is more difference between those two organisms as well. So organization then, we can also break that down into prokaryotes versus eukaryotes. So prokaryotes and eukaryotes. So prokaryotes are smaller. Eukaryotes are larger. So no membrane bound organelles. Eukaryotes have membrane bound organelles. Prokaryotes' DNA isn't contained in a nucleus. Eukaryotes' DNA is contained in a nucleus. What else? Larger, smaller. So they both have a cell membrane. So similarities is that they both have a cell membrane. We always talk about the differences, but they do have some similarities. They both have ribosomes. Ribosomes are not membrane-bound organelles, so don't forget that. We'll talk about that a little more later, though. So then also remember the difference between a theory and a law. So theory versus law. So a law is 100% true, whereas a theory then is a general explanation of a phenomena. So general explanation. So like 98% true. Whereas for it to become a law, it has to be 100% true. But don't think that just because someone says, oh, this is only a theory, saying it's only a theory is pretty good evidence that it's true. So don't get in that argument with someone. Now, don't confuse that with a hypothesis. So remember, a hypothesis is what you make in an experiment to figure out to support a theory. So let's say the light bulbs are out. You have a hypothesis that the light bulb is broken because the bulb is out. So you then can test that and replace the bulb and see if it works. So that's a hypothesis. Okay, now, so that's mostly that chapter there. And now we can go into the next chapter, which is on chemistry. So the big part of the chemistry chapter is understanding the membrane bound, understanding the electrons, the subatomic particles, and what gives something charge. So here, chemistry. You will have access to a periodic table during the exam, so that shouldn't be a problem. But just as a little review here, the subatomic particles are protons, neutrons, and electrons. Now, the ones that carry a charge, electrons are negative, protons are positive. If proton number changes, so if proton number changes, the element changes. So if we go from 6 protons to 7 protons, we go from carbon to nitrogen. So, but if neutron number changes, the element stays the same in a way, it just becomes a different isotope. So it becomes different isotope, not isomer. Isomer is something different that we will talk about later. So different isotopes such as carbon-12 or carbon-14. So carbon-14 is a popular one used in carbon dating. So then, final one here, if electron changes, the charge changes. So now we can start talking about what gives an atom a charge. So let's look at sodium. If we were to draw sodium on the periodic table here, so sodium would be Na. Sodium would have 11 up here, and this is around, 22 down here for the atomic number. So the 11 represents the protons. This is the atomic mass. So the total mass of protons plus neutrons. Electrons don't bring anything to the charge. So if we have 11 protons, which are positive, for sodium to be neutral, it must have 11 electrons. Because plus 11 minus 11, charge of 0. But let's say we remove 1 electron. So when sodium forms an ionic bond, an electron is transferred from a sodium to a chlorine. So in that case, sodium loses an electron, and now we have 11 protons still, but now we only have 10 electrons. So we have a plus 1 charge. So then sodium is written as Na+. So that's why we see it written as like that in ionic form, because it loses 1 electron. Now, if we drew the electron clouds around sodium, so it has 11. To be neutral, we know it needs to have 11 electrons. So the first orbit, first shell here, can only hold 2 electrons. Then we add the second shell, so sodium is in the third row on the periodic table, which means it has 3 shells. So the second shell here holds 8 electrons, and every shell past the first shell holds 8 electrons. So now we have 2 plus 8, we have 10 electrons, and we add 1 more electron out here for the 11th electron. So sodium and other atoms in the first column of the periodic table are the most reactive, so such as hydrogen, lithium, potassium, and so forth. If we have a full outer shell, we are inert. So if we were to remove this shell here and just have this, we are now showing, what is this, neon. So neon has 8 electrons in the outer shell, and this is an inert molecule. So it doesn't want to react in anything because an electron is most stable when all electron pairs are filled. It's most unstable when they're not filled. So 1 electron out there is very, very unstable. So it wants to form another bond. So let's say, first, an atom with no electric charge, then equal number of protons versus electrons. And then if we say a random number, so let's say we have, what's another? The sulfur. No, that won't form. Let's do fluorine. So fluorine is right after oxygen on a periodic table, and fluorine has the number 9 on it. So 9 protons. So for fluorine to be in stable, well, equal, no charge, it would have 9 electrons. So 9 plus 9 minus 9, 0. Now let's say I give you a fluorine atom with a charge of plus 2. And I ask how many electrons are in the valence shell. So I'll write that down here. If fluorine plus 2, how many electrons in valence shell? So how do we do this problem? First, we want to figure out how many electrons fluorine has. So if we know that if fluorine has an atomic mass or a proton number of 9, we can use that. So to get to a plus 2 charge down here, we would have 2 less electrons. So that's plus 9 minus 7 gives a plus 2. So that means we have 7 electrons. So we know 7 electrons total. This is the key, that's 7 electrons total. The question asks how many electrons in the valence shell. So if we look at where fluorine is on the periodic table, it's in the second row. So if we draw a fluorine atom here, the first shell has 2. Now we go to the next shell and we draw them. So 2, 3, 4, 5, 6, 7. So this would be a fluorine plus 2, where a typical fluorine would also have 1 there and 1 there. So make sure you be able to do those calculations and go any of the different forms of that question that could be. So I could ask this form, I could ask this form, so forth. So then the answer to this would be 1, 2, 3, 4, 5 electrons in the valence shell. So then also remember the difference between the electrons in a valence shell and an atom's valence. So let's look at nitrogen here. Actually, let's just look at a randomly bonded molecule. So here's molecule A, and this is simulating nitrogen. So here, 2 electron pairs here, 1, 2, 3. So right now, A, the valence is equal to 3. But valence electrons is equal to 1, 2, 3, 4, 5. So make sure you understand the difference between valence and valence electrons. Now let's say something else bound to this, and this is B. And the green represents the electron that belongs to B. So now B, the valence of B is equal to 1. So this would be like NH3 would be an example of that. So we'd have the nitrogen bonded to hydrogen, hydrogen, hydrogen. It just, these are those electrons then drawn out. And again, electrons are most stable when all electron orbitals in that valence shell are filled. So then make sure you understand the difference between a covalent bond, which is a sharing of electrons, a ionic bond, which is an electrical attraction of ions after the transfer of electrons. So after transferring electrons. Now we go into some other bonds. So hydrogen bonds Hydrogen bonds do not occur within atoms. Hydrogen bonds occur between molecules. So if we look at two water molecules, so let's draw two water molecules right here. And then this one is going to be flipped. So remember, water itself has what are called polar covalent bonds. However, so when we have polar covalent bonds, that means there's a partial negative here, partial positive here. So remember, this is due to electronegativity. So that's a polar covalent bond. This is a polar covalent bond. So is that, and so is that. Now what could form are hydrogen bonds. So polar covalent bonds can only form within a molecule. Hydrogen bonds form between molecules. So right here, a hydrogen bond involves a hydrogen and another electronegative atom. So right here, these dashed lines are representing hydrogen bonds that could have formed between these two opposite charges. So here then, this is a hydrogen bond. So hydrogen bond then can form between molecules, and that's what gives water all of its properties that support life. So high surface tension. So those water spiders can walk on water because of high surface tension. Evaporative cooling is a feature of water because of the making and breaking of these hydrogen bonds and its ability to absorb and release heat. So on a low, humid, and hot day, sweat evaporates also off of you, and you get a cooling sensation when that happens. So make sure you understand the difference between a polar covalent bond and a hydrogen bond. So, and also related to this, you can have non-polar covalent bonds. So if I draw a hydrocarbon, oops, let's go back to black here. So if I draw a hydrocarbon, so what's a hydrocarbon? Hydrocarbon is a long chain of carbons with hydrogens. Every dash here would be a hydrogen. I don't want to draw them all. We're going to come back to these later when I discuss the macromolecules. So these are non-polar covalent bonds, which makes this molecule hydrophobic. Remember, phobic is a fear of water. So things such as fats, oils, and other lipids, which have these long hydrocarbon regions, repel water because they are hydrophobic. Whereas molecules that are polar, can form hydrogen bonds, are hydrophilic. So then water can also dissolve ions. So let's say we drew an ion in the middle here. And now let's say on the outside of this ion, we have the water forming the hydration shell. I know this isn't too accurate here with the bond angles, but the key is what's facing towards the ion that's being dissolved. So remember, all the hydrogens have a partial positive and all the oxygens have a partial negative. Remember now, like dissolves like. So if I'd ask, what is the charge of this ion in the middle, and you know it's surrounded by all these partial positives, you know this has a negative charge based on the position of the oxygens or hydrogens around that molecule. So that's how we dissolve salt, sugar, and things like that in solution. 1 second, I need to get a sip of water. Hope you guys are all understanding things. Remember, if you're not understanding something at all throughout this, be sure to send me an email. And I'll try to get to it as soon as I can. So now that we're talking about water, let's move into pH, the part everyone hates. So pH. Now the extent of this is understanding the pH scale and how to calculate simple pHs based off of concentration. So first, pH scale goes from 1 to 14. We go this way on the scale. Hydrogen concentration increases We go this way on the scale. So here the middle point is 7. Hydrogen ion concentration decreases. So if first step here is if we were to graph how pH changes. So simple graph here on the y-axis. Let's do H3O plus. So this is the same as H plus. You see H3O plus is a hydronium ion. And then down here we have pH. So when hydrogen ion concentrations are high, so this then goes from 0 to 14, is pH lower or higher? So pH is at low pH concentrations, hydrogen ion concentration is higher. At high pH, they're lower. So now what happens in between? Remember, pH is equal to negative log H plus. That's a logarithmic scale, so pH is not linear. So pH follows a curve like this. So it wouldn't be a linear line coming down through there. So what this means, as pH increases, H plus concentration decreases. So the same example can be said, let's say we're slowly dropping. So when we have ocean acidification, we have CO2 entering the water supply. When CO2 enters the water supply, it releases H plus ions. So if we draw another graph here, and we now put pH on this axis, and let's say we have water, so then this goes from 0 to 14, and right here is 7. So water, we have a pH of 7. Now, right here will be time. So as we produce more CO2, CO2 is dissolved into the ocean, and H plus ions begin to increase. So as H plus ions increase, we begin to lower the pH. So then this would then lower down to here, if you were to draw that as a graph. So you can actually do that experiment in a lab if you add CO2 to a solution of water, and you can see the pH slowly drop over time as it creates H plus ions. Okay, so then also remember what it means from going from something like a 7 to a 9 on the pH scale. So 7 to a 9 on the pH scale, how many times more acidic or basic? So here, remember, so 7 to 8 to 9, every factor is by 10. So for this one, it's 10 times 10, which is 100 times. If we were only going from 7 to 8, it'd only be 10 times. But so every whole number change in pH is a 10-fold change. So if I was asking how many times more hydrogen ions are there in a pH of 7 than in a pH of 9, you would say 100 times more hydrogen ions. So that pretty much, how to calculate pH, duh. So last part for pH here is how to calculate it. So remember the equation pH equals negative log of H plus. I won't try to trick you on any of these, so just know the simple tricks. And also the other equation is H plus times OH minus equals 10 to the minus 14th. So let's say I give you H plus concentration is equal to 10 to the minus 5th. So you just simply plug that into this equation. So pH is equal to negative log 10 to the minus 5th, which equals 5. So if you type that into your calculator, it gives you 5 as an answer. Now the problem is, what if I say OH concentration is equal to 10 to the minus 5th? Now you can't plug that into the equation. So you'd first use this equation. But let me tell you a trick. So for this one, if you're given hydroxide ion concentration, just use pH is equal to 14 minus this exponent, so minus 5, that equals 9. So there's a little trick you can use for this process right here if you're given hydroxide ion concentration. Okay, now we move into carbon. I never labeled where we started water. I guess we talked a little bit about it both there. This works. So carbon. Why is carbon so important? It can form a diverse amount of large macromolecules because it can form 4 bonds. And if we go back, how did we initially make these organic molecules that we have on Earth? So Stanley Miller's experiment was the first one to abiotically, meaning without life, synthesize these organic molecules. He did not create life in that primordial goop experiment. So they mimicked the early conditions on Earth, lightning, ammonia, methane, and were able to make the basic organic building blocks that are needed for life. Not all of them, of course, but some. Like I said, hydrocarbons are insoluble in water because of these nonpolar covalent bonds, making it hydrophobic. So, and then when we draw bonds out here, just as a little aside, so if I were to draw a ammonia, not ammonia, N2 gas, so N2 has a triple bond. So how many electrons are represented in a triple bond? 6 electrons. So 2 electrons per line. So a covalent bond. So these covalent bonds here represent 2 electrons. If we were to draw O2 gas, not like that. So oxygen gas, which is O2, 2 oxygens, these represent 4 electrons. So make sure you know how many electrons are in each type of bond. Then back to carbon here. So one thing these different carbon molecules can do is have different isomers, not isotopes. So think of mer for molecule. Molecule. So isomers, you can have structural isomers. You can have cis-trans isomers. So cis-trans isomer is when you have a double bond in the middle, you have an X going up and X going down. So that X is just some random group, and then let's just draw hydrogen there. So this would be the cis version, and then the trans version would be the X's are now facing the same side. So these 2 molecules now have a different function based on what conformational shape that they're in. Structural isomers are just a completely random structure but same number of molecules. And then enantiomers are the last one here. Enantiomers are like your left and right hand, and they are mirror images of each other. Okay, now with carbon we have the host amount of functional groups. So what are the functional groups? First one is the hydroxyl. The hydroxyl functional group is OH. Next, we have the carbonyl. This one has 2 forms. It has the ketone, which is carbon, carbon, double bond, oxygen, carbon with other items. And then we have an aldehyde, which is carbon, carbon. Then its last carbon is what has the functional group on it. So that's a double bond oxygen. So for carbonyls, look for that double bond oxygen, but this one is in the middle. For a ketone, and aldehyde is at the end. And now we'll talk about the next one right after that, which is a carboxyl. So our carboxyl, or also known as carboxylic acid. This one, double parentheses, carbon, carbon. Let's just do another carbon here just to keep it like that one. It's another double bond oxygen, but in here, instead of an H for an aldehyde, it's an OH. Sometimes you see this written as the Cu group. Next one, we have an amino group. That is the N NH2. Yeah, NH2. So that's typically written as carbon, carbon, NH2. Then we have the methyl group. That's CH3. See methylation happen a lot. And then we have the phosphate group. So the phosphate group is, oh, hold on, we have phosphate and then sulfhydryl. Can't forget that one. So phosphate is where we have, let's see, carbon, oxygen, what's it go? Phosphorus, and then it's oxygen negative, double bond oxygen. Again, you don't have to worry about how to draw this. Only I do right now. So right there, that's the phosphate group. And this one is the energy currency molecule, or energy. I was trying to combine energy and currency in the same word there. Functional group. This is what we find on ATP. And then the last one that I can think of off the top of my mind right now is the sulfhydryl group, which is SH, which is important in forming disulfide bonds. So now we can start doing different reactions and building organic molecules, which was the most recent chapter we had on all this. So now let's talk about macromolecules. Not molecules. Molecules. So first, what are the major ones of life? We have carbohydrates, so carbs. Then we have lipids. We have proteins. And then nucleic acids. Now, carbs, proteins, and nucleic acids are all made of monomers, which grow to polymers. So how do these work? So what are the two main reactions? So what is a dehydration versus hydrolysis reaction? So make sure you understand the main difference between those two reactions. So the best relationship is that a dehydration reactions assemble polymers, hydrolysis reactions break them. So assemble polymers, and from this water is removed, and these ones break, wrong form of break polymers. In this one, water is needed. So water cutting, water splitting, dehydration is water removal. So there are times where we want to make polymers and times where we want to break polymers depending on the situation. So an example where we break down a polymer is when we break down starch into individual glucose monomers so that we can absorb it. Now there's a form of this that we cannot absorb, and it's called cellulose. So cellulose can't be broken down because we lack enzymes that can break down beta glycosidic linkages. So humans can digest starch, but not cellulose, because humans have the enzymes that can hydrolyze the alpha glycosidic linkages of starch, but the beta glycosidic linkages of cellulose cannot be digested because of how they form over each other. Then amylase cannot get in there and break it apart. So that's why they pass through our system as undigestible fiber. So think of beta equal bad. It's a horrible way to remember it, but bad meaning can't digest. So beta glycosidic bond. So that leads us into carbohydrates. The bond between two carbohydrates is, so carbs have a glycosidic bond. Proteins, peptide bond. We'll diagram one of those coming up. Lipids, you don't have to worry about these two as much, but this is an ester bond. Nucleic acids have a phosphodiester bond. Again, these two aren't as important. It's mainly peptide bond and glycosidic bond should be part of your vocabulary. So I wanted to make sure to mention those. So another example, so with carbohydrates then, carbohydrates are made up of monosaccharides. And when two monosaccharides come together, it's called a disaccharide. So a popular disaccharide, an example of that is lactose. So lactose, people who are lactose intolerant, they can't break down the disaccharide. They can't break that glycosidic bond in lactose. So they have the issues with it because they lack the enzyme lactase. They don't have lactase and they cannot digest lactose, and that's what causes GI distress. So all carbohydrates have the form CH2O. So let's say we have 6 carbons, it'd be 6 C6H12O6, which would be glucose. So now we move to lipids. So for lipids, make sure you understand. So lipids, saturated versus unsaturated. So saturated, all single bonds saturated with hydrogens. Then unsaturated has double bonds. So let's just draw a double bond in the middle. Now hydrogen's there, so we're missing a hydrogen there and a hydrogen there. So no hydrogens on those and then there. So this is no longer saturated with hydrogens, hence its name. So solid at room temp, RT is room temp, and unsaturated are liquid at room temp. And that deals with how these bond angles that form from this double bond. It makes it so they don't stick together as much. So unsaturated fats are better for you than saturated fats. The worst fats for you are trans fats, but I'm not going to be testing you on that. So make sure you understand that difference. And then we have another lipid here. So what makes up a fatty acid? So a fatty acid has a hydrocarbon chain. It can be vary in chain length and have different varying double bonds. And then at the end here, we have a carboxylic acid group. So this would be a fatty acid. And then a triglyceride then binds this down a glycerol head, and then you can have 3 fatty acids that come together forming those ester bonds. So then the other type here is a phospholipid. I'll just write it over here. So a phospholipid has a polar head and nonpolar tails. So those tails don't typically draw them like that, but they are hydrocarbons. So these are nonpolar, hydrophobic, and over here we have a polar head because up here there's oxygens, which are partially negatives, and then a nitrogen, which is also partially negative. So here we have a partial negative charge up here, and then down here it's nonpolar. So if we put this in the presence of water, it's going to self-assemble into what are called a lipid bilayers, and that's why all of our membranes are made up of a phospholipid bilayer. So the nonpolar tails do not interact with water, and the polar heads do. So now we can talk about amino acids a little bit. Oh, so the other lipid are the steroids, and I won't ask too much about steroids, but if you ever see something like cholesterol and has that 4-ring carbon ring complex. Can't draw it off the top of my head right now, but that is also a lipid. So now we can move to proteins. Remember, proteins are made up of 20 amino acids. Now, what component varies among these 20 amino acids? So every amino acid has a central carbon. They also have a carboxylic acid end, and they also have an amino end. down here is a hydrogen. Now the part that varies is this R group. So this varies with every single amino acid. This is known as the N-terminus, hence the nitrogen. The amino end is the N-terminus, or N-terminal. You might see it written both ways. And then here, this is the C-terminus. C for carboxylic acid. Now, let's say we put another one right beside it. So central carbon, the amino group, hydrogen, hydrogen, other carbon, hydrogen, carboxylic acid, and R group. Now I'm going to erase this part here, but don't forget it. Now let's form a peptide bond. Remember, a peptide bond is what brings amino acids together. Now what happens here is we have a dehydration reaction. So if we draw this reaction coming down, water is removed. So that water actually comes from right here. So that OH and that hydrogen release water. Now this bond will form between that carbon and that nitrogen. So if we were to draw this bond then, this dipeptide, we'd have an oxygen, we have a nitrogen, and we have a carbon here. There'd be one hydrogen coming off there. This carbon will go up to the R group. I have a hydrogen here, carbon, double bond, OH, and then here is the remainder on this one, carbon, R, and then here is the NH2 group, the amino group, and then hydrogen. So this peptide bond. So here we have two amino acids, one peptide bond. So a dipeptide has one peptide bond. A tripeptide has two peptide bonds. So that's most of what you need to know about proteins. Not a lot of information on that, but it's important to understand the basics because I will refer to proteins a lot throughout the rest of the semester. There's also things such as protein folding. So we have primary, secondary, tertiary, and quaternary. The different levels of protein folding. So primary is just the chain of amino acids. Secondary, look for the words alpha helix and beta sheet form. Tertiary is side chain interactions, so disulfide bonds, hydrophobic interactions, ionic bonds, van der Waals forces, and so forth. And then quaternary is polypeptide formation. So polypeptide, multiple polypeptides come together. So multiple proteins come together for it to be active then. So like hemoglobin has 4 subunits that need to come together for that final functional structure. So next we can move into nucleic acids. So first part is, what's the difference between DNA versus RNA? So it comes down to that ribose sugar. So DNA, if we just draw the sugar for each, boom, boom, let's see if I get this right. DNA is OH with an H here. I believe this is an OH coming off the top there. Well, we can just draw the DNA then. So this will then go to the base. Then up here, this will then go to the phosphate group. So a nucleotide is a sugar. This is deoxyribose on DNA. A sugar, a phosphate, and a base. This is a nucleotide. So nucleotides are the monomers of nucleic acids. So if this is DNA, and I were to draw RNA over here, RNA is a ribose sugar, meaning the only difference is this hydroxyl group instead of that hydrogen. Again, a base and a phosphate group. So this is ribose, and it's another nucleotide. So this one's DNA, this one's RNA. So that's the difference between the two. So it's a type of sugar that differs. And remember, the central role in molecular biology is, or the central dogma, DNA gets transcribed or translated. This is transcribed into RNA, which is then translated into protein. And then the other parts, just understand the basic structure. So if I show you a sugar, understand it's a carbohydrate. If I show you a hydrocarbon, know that it's going to be a lipid, and so forth. Understand the general structure of an amino acid so you can pick an amino acid out of a group of structures. So that's mostly it. Let me scroll through my cheat sheet here and make sure I mentioned everything. But watching that and understanding everything I talked about should get you a decent grade on the exam. Oh, a few other things. Let's go back here to the beginning and just scroll through. So evolution here, a little bit about that. Who is known as the father of evolution? Remember this, Charles Darwin. Chemical equilibrium. So what is chemical equilibrium? That is when the rate of the forward reaction is equal to the rate of the reverse reaction. In terms for water, remember ice is more dense than liquid water, so it floats. The difference between cohesion and adhesion for water. So cohesion is when water molecules stick to itself, whereas adhesion is when water molecules stick to the surroundings like adhesive tape. And yeah, I think that covers mostly everything you guys will have to know. And I think that should be a good summary of it all. So I'm going to post this on Canvas, and like I said, you have the captions to go with this, and it should help you a lot on your exam. All right, guys, if you have any questions, feel free to let me know. If not, good luck on the exam, and have a great day.